The same binary question gate now repeats. On each independent trial, it outputs 0 with probability 9/10 and 1 with probability 1/10. The order of those outputs is part of the message. The sender sees the ordered results. The receiver knows the 90-10 source rule, but not the realized sequence. The sender may replace a source block with a variable length binary word. The receiver must reconstruct every output exactly, and we score the average transmitted length under this source model. First, encode one source output at a time. 0 and 1 need distinct complete code words. The shallowest binary prefix tree has 2 leaves, each one edge from the root. So every source output costs 1 transmitted bit. That conclusion is correct for this one output coding unit. Now the source produces 100 outputs. Can an exact code represent this block using fewer than 100 transmitted bits on average? Place your estimate on the ruler.
I choose 100 bits. Every position is still either 0 or 1, so I think each position still needs 1 bit.
The 1-bit argument fixed a code word boundary after every source output. But the receiver needs the ordered sequence, not those intermediate boundaries. Let us make 2 consecutive outputs one coding object and test the conclusion again. Keep the output order and place a bracket around each pair. One pair has 4 possible identities. 2 zeros occur with probability 0.81. 0, 1, and 1, 0 each occur with probability 0.09. 2 ones occur with probability 0.01. Give the common 0, 0 pair the shortest complete word. Give 0, 1 a 2-digit word, and give the remaining pairs 3 digits each. The exact digits stay on screen. Follow the pair 1, 0. Its 3 transmitted digits end at 1 leaf, so the receiver restores both outputs in their original order. No completed word begins another, so the stream remains unambiguous. Multiply each word length by its pair probability. The exact terms are on screen. Together they give 1.29 transmitted bits per pair. Because each pair contains 2 source outputs, that is less than 2/3 of a transmitted bit per output.
The 1-bit limit was true for one output, but grouping changed the object that receives a code word.
Return to a block of 100 outputs. This particular illustration contains 10 ones, but the source does not promise exactly 10. Every one of the 2 to the 100 ordered binary sequences remains possible and must have an exact representation. For analysis, group possible blocks by their number of ones without rearranging any realized message. The height of each bar is the total probability of all orderings in that group. For this independent 90-10 source, the probability mass peaks near 10 ones and falls away on both sides. The group with exactly 10 ones contains more than 17 trillion different orderings. Each particular ordering has probability about 2 to the minus 46.9, while the whole group carries only about 13% of the probability. One group is not the whole answer. The useful region also includes nearby compositions, and its clean size law appears only as the block grows. Before naming the high probability region, price one source output. We use the negative base 2 logarithm of an outcome's probability as its ideal surprise bill. A 0 has probability 9/10, so its bill is about 0.152 bits. A 1 has probability 1/10, so its bill is about 3.322 bits. Weight each bill by how often its outcome occurs. 9/10 times the 0 bill plus 1/10 times the 1 bill equals about 0.469 bits per output. This average bill is the source entropy. Now let the independent source run for a long block. Most of the probability gathers on blocks whose average bill per output is close to that entropy. We call this high probability collection the typical region. As the block grows, the chance of landing in that region approaches 1. For an independent block, the individual surprise bills add. A typical block, therefore, has a total bill near the block length multiplied by the source entropy. That means one such block has a probability near 2 raised to the negative of that total bill. The typical blocks together carry almost all the probability. If nearly 1 unit of probability is shared among blocks of roughly that size, their count must be near 2 raised to the block length multiplied by the source entropy. The full binary space still contains 2 raised to the block length blocks. The source simply places most of its probability on a much smaller collection. Typical does not mean most probable by itself. For the 9010 source, the all-zero block is the single most probable block, but it never contains the usual 1/10 share of ones, so it falls outside the ordinary long-run collection. The word typical names the collection carrying nearly all the probability. Its scale is about 0.469 bits per output, or roughly 46.9 bits per 100 outputs. Now use 2 roots. When a block belongs to the typical region, send 1 flag followed by a short number identifying that block. For every block outside the region, use the other flag followed by a longer literal representation. Both roots end at the same exact receiver, so no possible block disappears. The longer exceptions are rare under the model. They are also necessary. There are fewer binary words shorter than n than there are n-bit inputs, so no injective compressor can short every input. The exact limit is even cleaner. Treat the complete length n block as one random object and ask for its best binary prefix code. The best average length cannot fall below the block entropy and can be kept less than 1 bit above it. Independence makes the block entropy equal to the block length multiplied by the source entropy. Divide by the block length, and the extra rounding allowance is less than 1 bit divided by that length, per source output. For the 9010 source and a block of 100 outputs, the entropy is 46.899 bits. The best exact binary prefix code therefore averages at least 46.900 and less than 47.900 transmitted bits per block. So the answer to the opening question is yes. The average can be far below 100. This is an average length promise with exact decoding. It does not promise that every 100 output block uses 47 bits. Likely blocks take the short route, while every exception keeps a longer route. We have explained the lossless average limit, not a specific compression algorithm. Keep the binary alphabet, independent repeats, exact receiver, and 100 output block. Change only the probability of 1 from 1/10 to 1/4, should the best achievable rate move up or down.
It should move up. Ones are less rare, so the source is harder to predict, and the high probability region should contain more sequences.
That prediction is correct. The likely compositions spread around 25 ones instead of 10. On the binary entropy curve, the rate rises from about 0.469 to 0.811 bits per output. For 100 outputs, the exact prefix average is at least 81.128 and below 82.128 bits. The alphabet never changed. The probability model changed, so the number of likely distinctions changed. Entropy is where exact lossless compression stops on average for that model. The next question is what happens when the source follows one distribution, but the code is priced for another.